In this video I'm going to show what the inverse trig graphs look like. These are mainly y equals sine inverse of x, y equals cosine inverse of x, and y equals tan inverse of x. But before I do that, I just want to show some general things about inverses of graphs in general. Here's an example of a function, f of x equals 2x plus 3. If I plug something like 5 into the function, I end up with 13 comes out of the function. The inverse function, f inverse of x, well, one thing we can say about that function is that if I put 13 in, it should make 5 come out. In general, it's a little complicated at first if you think about like what needs to happen to the 13 to become that number 5. Well, the 5 became the 13 in this function by adding 3 and then by doubling first and then adding 3. So to turn it back into the 5, you have to take away the 3 and then divide by 2. This is the inverse function. There's actually a process for creating inverse functions. You might remember where you start like this, then you switch the x and the y, and then you isolate the y to get the inverse function. Now if you come over here and you graph the original function, 2x plus 3, something like that, notice that, for instance, one of the points on this is, or would be, if I made it properly, would be 5, 13. So the inverse graph is going to have 13, 5 on it. And any point on the original, there's going to be sort of a partner point on the inverse. Well, if I graph the inverse graph, which was the inverse was x minus 3 over 2, which is 1/2 x minus 3/2. So it looks something like this. 3/2 is down here. Slope of a half. Something like that. And what I want you to notice is that for every point, like 5, 13, there's a partner point, 13, 5, that has the x and y values sort of swapped around. And in general, if I make the line y equals x, those two graphs will be sort of symmetrical with respect to the line y equals x. And they actually meet up at a point. That's the point where x is equal to f of x, which I suppose is x equals 2x plus 3 at x equals negative 3, and y equals negative 3 also. Now if you take a more complicated function, f of x equals x squared, that's going to form a parabola. It's a lot skinnier of a parabola than most people think when they just try to sketch it by hand without using graph paper. Now, an example of a point on this function is the point 3, 9, because f of 3 equals 9. So there should be a point on the inverse. F inverse of 9 is equal to 3. So I should have this point 9, 3 over here. And another point is 2, 4. So there should be a point 4, 2. And what we end up with, if we do that for every point, we would end up with a sideways parabola. Basically, this parabola has been actually they actually meet up at the point 1, 1. But there's a bit of an issue here, which is this. I have the point 3, 9, because f of 3 equals 9, but f of negative 3 also equals 9. So when I try to do f inverse of 9, should I get 3 or negative 3? Well, in one sense you could say they should both come out, but in a function only one thing can come out, and if you look at the graph here, this green one is not really a function at all because it fails what's known as the vertical line test. So there's a sneaky way around this. We really wish this thing would not fail the vertical line test. We really want to get just one answer, but which one? Should it be 3 or negative 3? Well, the way they figured out how to get around this is not to actually fix the inverse, but to alter the original function. You see, the inverse fails the vertical line test because the original fails the horizontal line test. So if I do something that's called restricting the domain, I also end up restricting this here. So the way we show this is we take the original function, f of x equals x squared, and we put a comma and say x is greater than or equal to 0. Now everything's fine. The inverse, f inverse of x, is the square root of x. And everything's fine now because I actually can't say what's f of negative 3 anymore. F of negative 3 is undefined now because of this domain. So that's called restricting the domain. Restricting the domain is when you make an original function pass the horizontal line test so that the inverse passes the vertical line test. Now a function that really fails the horizontal line test is something like sine x, where any horizontal line is going to pass through an infinite number of points. And so an example of a point on this graph would be sine of 30 is 1/2. I'll use radians, so sine of 30, which is pi over 6, is 1/2. So I have this point here. On the inverse graph, I should have the point 1/2 comma pi over 6. Which is a little hard to place, but it's not that far from this point. Now, if I drew the entire inverse, if I did that for every point, what we'd end up with is something like this. That green thing. If I took every point on this red curve and switched the x and y coordinates so that this thing was symmetrical around the y equals x line. But I don't want to have that because then I have to, if I ever want to say something like what's f inverse of 1/2, I want to get one answer, which is pi over 6. When in reality there's an infinite number of answers. If I look over here, I'll get more answers, but I want just one answer. So what we're going to do is we're going to restrict the domain so that the sine curve, the original one, is going to pass the horizontal line test. And I'm going to back up a bit all the way to here. Now, there's a lot, you might think, oh, okay, I'm going to just take this part. But that part actually fails the horizontal line test also, just this one little hill here. So and you might say, well, why don't I just take just this portion from 0 to pi over 2? But that leaves off some information. So the trick is to keep this portion from negative 90 to positive 90, or if you want to think radians, from negative pi over 2 to pi over 2. And now the inverse, which is actually pretty tricky to visualize, but it looks something like this. So that little thing there, that little green thing, is the inverse, and it's actually part of a sort of sideways sine curve. You want to just sort of picture that, even though the dotted line is not part of it. So now if I say f inverse of 1/2, here's 1/2. If I go here, there's only one point, and it's going to be pi over 6. But this also means something new. If I say f inverse of negative 1/2, if I go to negative 1/2 on the x-axis for the green curve, I end up with a negative y-coordinate. So I'm going to get negative pi over 6. And that's what happens with the, called the sine inverse function. You say sine inverse of 1/2 has one answer, which is just for 30 degrees, whatever you like. But sine inverse of negative 1/2 is going to be negative 30 degrees. So you take sine inverse of a negative number, you're going to get an angle between negative 90 and 90. We say that the domain of sine inverse is negative 90 or negative pi over 2, if you like. Also, the x value for that is between negative 90 and 90. Now I want to compare this to something that looks like almost the same idea, which is sine x equals 1/2. We usually think of this thing as having two answers, and it does have two answers. X is equal to 30 degrees. If you like a unit circle, here's 1/2, and also x is equal to 180 minus 350 degrees. So that's true. But if I say sine inverse of 1/2, that's only going to have one answer, just the answer that's between negative 90 and 90. On the other hand, if I say sine x equals negative 1/2, whether you like to picture this or whether you like to picture this, this has two answers. Reference angle's 30 degrees, but it's 180 plus 30 and 360 minus 30, so it's 210 or 330. Those are the two answers to this question. But if I say sine inverse of negative 1/2, the answer is not 210 or 330, but it's negative 30 degrees, because the answer to a sine inverse question has to be between negative and 90 and 90. Now we can do a similar thing for cosine. Here's the graph of cosine x. And see, I have this point over here, which is 0, 1. That means that on the cosine, on this other graph, I'm going to have the point 1, 0. That corresponds with this one. And over here, I have the point pi over 2, 0. And on this one, I'm going to have 0, pi over 2. So I end up with actually something like this. That's if I'm doing the entire thing. But I don't want the whole thing, because I want to be able to say what's f inverse of some number, like f inverse of 1/2, I should get 60 degrees, or pi over 3. But right now, if I do the inverse of 1/2, I get so many answers. So I'm going to restrict the domain of the original. And we have to make a decision here. So the graph is going to look something like this when I take this portion of the red curve that passes the horizontal line test, and it turns into this portion of the green curve, which passes the vertical line test. Now, when you say something like, what's cosine inverse of 1/2? Well, if I go to 1/2, and I go up here, the y-coordinate is going to be 60 degrees. If I say cosine inverse of negative 1/2, it's not going to be negative 60 degrees as you might expect from what we saw with sine. If I go to negative 1/2, I end up here, and it ends up being between 90 and 180, and it's 120 degrees. Now this agrees with this kind of question somewhat. If I say cosine x equals 1/2, we'd have like reference angle is 60 degrees, and cosine is positive in quadrants 1 and 4. X equals 60, x equals 300. But that's different from saying cosine inverse of 1/2, which only has one answer. So this question has two answers, 60 and 300. This question written this way has only one answer. And finally, if I say cosine x equals negative 1/2, that equation has two answers. Reference angle is 60 degrees. I'm here in quadrant 2 and 3, so the answers are 120 or 240. But if I say the question this way, it looks like the same question, cosine inverse of negative 1/2. That's going to have just one answer, because cosine inverse has got to mention this, cosine inverse has a domain actually I mean a range. I mean the domain is still from negative 1 to 1. That's true for the sine one. I think I said that inaccurately before. But it's the y value. For cosine, it stays between 0 and 180. And that's why the answer for this last question is not negative 60, but it is positive 120. It's basically the quadrant 1 and this is the quadrant 2 answer. But for sine, it was like quadrant, if you want to call it, the quadrant negative 1. It always ends up being when this is negative. So it's a little confusing, but that's the way that works with the inverse graph for sine and cosine.